All right, so what I want you guys to do is pick out a random sample of 5 students. How should you pick out a random sample here? Random number generator. You're going to tell it to go from 1 to 21. Write these scores down and number them on your page somewhere just so you have some reference here, so you're not counting which one is number 16. Write them down and label whether it's number 1, number 2, number 3, number 4, number 5. And then use that random number generator to pick out 5 students. You're going to record their scores on the first line, and then you're going to find the average of those 5 scores. Then you're going to do the same process again. And then you're going to do it again. And then you're going to do it a 4th time. So you're going to end up taking 4 samples of 5 students and finding the average of those 5 scores. Use your random number generator to pick out which scores you are using for your random sample of 5. Real quick, before you guys get too deep into this, I want to finish the instructions so I can set you guys loose on this part. So you'll use your random number generator, 1 through 21, to pick out 5 of those scores. You'll take those 5 scores, you'll write them down on the line. You'll find the average of those 5 scores. You're going to do that 4 times over. Once you are done with that, I'm going to give you guys 4 little dot stickers. On each one of these dot stickers, you're going to put one of your means, one of your averages. So 1 sticker for each of the means on those 4 lines. And then you're going to come up here to the poster that I have on this easel, and you're going to put your dots where they would fall on that number line for your averages. All right? I'm going to come around and pass out the dot stickers. If you are still confused about what it is that I'm asking you to do, please raise your hand and let me know. All of them go on that line together. And then you do that there as well. And then again over here and again over here. So you should end up choosing a total of 20 numbers, and it's okay if you have repeats in there.
You said we do it
You pick out a random sample of 5. You write down all 5 of those numbers on this line.
Yeah, I don't want to know. We just do it 4 times.
And then you do it 4 times over, yes. Yeah, there's Kevin there on my desk.
Wait, is it with or without replacement?
It can be with replacement, yes. So you can choose the same student score more than once. Right over there, dear. Yep. That's what you're going to write on the line, but on the sticker, you're just going to put this number. So on the line, you'll write down the 5 numbers so that you can justify how you got that mean. But then on the dot stickers, you're just going to put what that average is, what that X bar is. Hmm?
So just go ahead and put them.
Yeah, so you want to write the number, your mean number on each of those stickers. So you should have 4 different means, and then go up and put them where they belong on the graph.
Oh, did he write the number?
Yeah, you want to write what your average was on each of those stickers.
Do you want us to write the whole numbers?
Nope, it's okay to write decimals on there, and then you'll just put it in the closest spot that you can. Mm-hmm. You don't think you got stickers? I'm so sorry. There you go.
So you said 1 through 21, right?
You choose a random number generator for 1 through 21.
I think I did something wrong.
Because you're not averaging 1 through 21. You're averaging the scores that are up there. So your random number generator, these numbers right here, you're going to go find score number 1. That's 64. Score number 11. Count up there which one is score number 11. So these are your random numbers. That's not what you're averaging. You're averaging those. Look, score number 1, you need to write that down on the line because that's score number 1. And then for 11, you do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 11, so you'd write 86 down on the line. So you can keep the random numbers that you have there and just match which score they go with, and then average those numbers. You can go through and answer question number 2 after you're done with your averages. If you're all done with your averages and you've already put your stickers up there, I want you to try to answer question number 2.
Yeah.
You're supposed to write it.
Oh, you're supposed to write on
Yep, you're supposed to write your averages on the dot. Yep, you write it on the dot and then you bring it up here.
Now, how am I supposed to? There's no room.
Just then go up.
I think she's too.
Remember, dot plots go up like these guys. So just like, if you can't get it exactly on the number because there's another dot sticker too close, just take it up higher. Because if we'd made our buckets a little bit bigger, like a little bit smaller, they'd all be stacked on top of each other. All right. We need to get the rest of these dot stickers up here. So if you have not put your dot stickers up, please go ahead and finish your calculations. And then bring your dot stickers up. Make sure you don't put a sticker on top of another sticker. Oh, yeah, I'm so sorry. Yes, there you go. You all finished? All right. I'll have you pick up and join us from here. We probably don't have time for you to do the averages, but then you can pick up and still get the rest of this activity. Do you need the packet, or did you grab that on Friday? Okay. Right there on the left, you need that. Nope, on the left. Sorry, on the right. Yeah. You need that paper and you need the packet below it. Nope, nope. Right below where you just grabbed those papers. No. Same pile. Underneath. There you go. That's okay.
Oh my god. Lacey. That happened when I said energy.
What'd you say? I had it done when I went to Hawaii this summer by a local artist. So.
I mean, I have one. Like, I just got one. Like almost 3 weeks ago.
Nice.
Yeah, that's cool. I like that.
Yeah, it turned out really, really nice. I did have a little bit of scarring, but that's mine, not his. So
yeah,
that's just my skin. So.
That's so.
But yeah, it's nice, clean lines.
Yeah. How long did it take for that?
About an hour total from setup to sitting to everything. Yeah. All right. We have a lot of our stickers up here yet. Now we don't have quite all of them yet.
I was supposed to copy all that down. Yeah, I was about to say, like, I'm already.
You don't have to get every single dot on there. Get the basic shape. Get the basic shape.
So like
Because we have a ton of dots up there.
Oh yeah, we do.
I'm gonna try to figure out how many dots we have total.
Wait, aren't we just supposed to multiply everybody by 4?
Hmm.
You take everybody in class and multiply by 4, or no? You see how many dots we have right there?
Well, that's assuming everybody put theirs up. So I should be able to get a ballpark, but I'm gonna go up and count them anyway.
Oh, no, where do we go up to? 100?
There should be 68 dots total. If there's not a spot for you to put yours exactly, just put it above where it's closest. Awesome. Thank you, thank you. So get this basic shape copied down. So we should have how many? 68. Let's see. Yep. All right. So we're getting our basic shape up here. I'm going to see if it'll let me add this to my image over here. Yep. It's helpful then for when I'm putting it up as notes. All right, there we go. What should we label this? What is this? It's a dot plot. It's a dot plot showing what? This is a district. Is this all of the possible sample means of size 5? No, so we're going to call this the simulated sampling distribution of X bar. Simulated sampling distribution of X bar, because every single one of these dots is an X bar. Remember, X bar just means a mean from a sample. So we found the average from a sample. We did not calculate the average for the whole class last year. So I want to write down, like I have on here that I'm pointing to each dot, and that's an X bar, but more specifically, what does each dot represent? Sampling mean of what? Like, what did you do to get the number that's on that sticker? So 5 randomly generated numbers so that you could pick out what? You came up with 5 randomly generated numbers so that you could do what with the scores that were up on the top? So that you could what? You didn't find the mean of your random numbers. You found the mean of what? Of the scores. So each dot is a sample. Oops, if I could spell. Specifically a random sample, sorry. A random sample of 5 students and the mean test score calculated for that sample. You use the random number generator to pick out 5 students or to pick out 5 students' scores. And then you calculated the mean of that sample. And that's what went on each one of those dots, right? So looking at this, where would you ballpark, where would you make your best guess as to what the true test average was for the Chapter 6 test last year? You think it's about 78? Anybody agree or disagree with Akeem? You disagree with yourself? Does anybody else agree with 78? All right, I've got at least one person agreeing with 78. I'm going to go ahead and draw that line on the picture up here. So 78 would be about right here. Does that look like it's about average? It has kind of a left skew to it, right? But if it was more symmetric, would you feel okay about that? Yeah, I think that's a decent guess. So our guess, I'll tell you in a minute, from you is 78. Anthony agreed with you. Guess from you is 78. You guys want to know what the actual class average was? 78.48. For real.
Look at me. See, look. Sorry, my
The actual average for the Chapter 6 test was 78.48. So, what do you think? Do we have an unbiased estimator for the population average here? Yeah. I mean, I'm not going to add all 68 of those little numbers together and divide by 68, but we could to find out what the actual mean of our sampling distribution is. But just from a visual, we got pretty close to what the actual population average was. So we're going to go ahead and write that down too. We have an unbiased estimator. Unbiased estimator from you. From you. The mean of the sampling distribution is approximately equal to mu. That's what it means to have an unbiased estimator. I'm going to go ahead and draw that on here. Let's not use green. That'll blend in too much. Let's try red. Sorry. There, that way when we are looking at this again later, it makes sense. Did we take every single possible sample of size 5? No, we have 68 dots up here. How many samples of size 5 are possible? Or how would I figure that out? Yes, we're going to do NCR. We're going to do a combination. So I'm going to say, no, we didn't take all possible samples. So what would I put in front of the C? 68? 21. We'd put 21 because we had 21 scores to pick from. And we chose how many? We chose 5 each. How many possible samples of size 5 are there? 20,349 possible samples. Do you see why we didn't find them all? Yeah, that would have us here all day. To get a true sampling distribution, we would have to have all 20,349 samples. That's why we say this is a simulated sampling distribution, because we didn't get all 20,000 of them, but we got enough that we can see the basic shape of this. Yeah, if we had all of them, then we would have the sampling distribution of X bar.
Okay.
When we do some of them, in this case we did 86, just enough to get a feel for what this looks like, that's a simulated sampling distribution. It's not the actual thing, it's a simulation of it. If we took a random sample of 5 test scores at Rockford High School and we got a mean of 68, would we have convincing evidence that Rockford students did worse than the students at our school? Or is it possible that Rockford has the same average? All right, so I want to go back and look at this picture. Rockford had a score of, what, 68? Their average was 68. So that would be, what, right here? Yeah, there's nothing that's exactly 68 on our graph. We have this one right here is 63. Oops, this one's 63. Oh, you guys can't see that at all. That one's 63. This one is 65.4. We have 66.8 right here. This one is 65 even. And this one is 67. Everything else is greater than 68. On the other side, we have 70.2 and 68.8. So how many scores from our sampling distribution were the same as or less than Rockford? 5 out of? How many dots did we have? So 5 out of 68. I'll come back over here. 5 out of 68. Can somebody divide that on their calculator for me and give me a decimal approximation? 5 out of 68. 0.0735, something, something, something. So, do we have convincing evidence that the Rockford students did worse than the students at Pike? No. Why not? It's not 5% or less, yes. So no. And I would say, well, the Rockford average of 5 scores is low, five out of 68, so 7.35% of Pike's scores are 68 or lower. This is not rare enough or not unlikely enough to conclude Rockford did worse than Pike. If we'd gotten below 5%, then we would say, yeah, we have convincing evidence that the Rockford students did worse on this test than the Pike students. Let's go ahead and flip this over. So, when we are evaluating a claim, in this case, that's the last thing that we did. We evaluated the claim of whether or not the Rockford students did worse than the Pike students. We're going to assume that the claim is true. We're going to create a simulated sampling distribution, like we did right here. We're going to find the percent chance of getting the observed result. So that's where we marked off that 68 on the graph and counted all the dots that were that big or smaller. If my percent of dots is less than 5% against the simulation that I have, then we have convincing evidence against the claim. If it's more than 5%, we do not have convincing evidence against the claim. So in this case, we made the assumption that the Rockford students did the same as us. Thank you. We made the assumption that Rockford and Pike had the same average test scores overall. We created a simulated sampling distribution for test scores. We marked off right here where our dividing line was, there at 68, and we calculated that percentage. I'm gonna move right out of the way. Oh, it's too little?
I can't see that yellow.
Oh, that. Yeah, I just did what was up on the that I did on the screen. I'm just adding it to the poster for later. Yeah, no, that's way too difficult to read. Thank you, though, for pointing that out. Yeah, all I did was add to the picture this right here. I wrote 5 out of 68, and then I wrote what that percentage would be. I want you guys to give the check your understanding a try. We're going to take about 5-ish minutes. I know that might mean that you don't get all the way through it, but take about 5 minutes, and then we'll start going through this together. Yeah, basically. It's made, the interior of it is made out of an alloy, and it's like got a copper plating on the outside. Mm-hmm. Copper got too expensive. A penny was worth more than a penny.
My dad was
Did you say your dad wasn't even born yet?
Yeah, 1982.
I'm not old. Not old. I was already around.
Huh?
I said I was already around.
My dad was born in 85. My mom was born in 87.
Wow.
Yeah.
My husband was born in 86.
They're still in their 30s. Makes me feel old.
Makes you feel old?
Yes.
How does that make you feel old?
Because when I'm 20, my mom was going to be 30.
Yeah.
That's young. Like, they make you feel
Mm-hmm.
Yeah, I'm 16.
5.5.
Yeah, he is. My dad's going to be 49.
It's not old at all. You know,
Right,
Maybe
like, that's
like
so-
what?
That's so close to like my
Right,
age.
like, I'm sorry. Both my peers are already.
Oh, dang.
Really depends. Like my oldest is 24.
24?
So I had him when I was young.
Like, grown.
Yeah. Like he's grown on his own. And then I also have a 7-year-old. So
That's a large margin.
yeah. I got more than just 2 kids, so there's some in the middle there.
Oh.
But my oldest is 24 and my youngest is 7.
Yeah.
It has been a hot minute since we've done population and sample. What would the population be here? All the pennies inside the container. What would the sample be? 11 pennies? The 50 pennies. They counted, they found 11 out of the 50 that they sampled. Do you guys remember the difference between a parameter and a statistic? No. Parameter and statistic, we're calculating the same thing. Yes. So my parameter, what number up here is describing the population? Yeah. Jenna reads online that 13.2% of pennies in circulation are pre-1982 copper pennies. So the claim that's being made is that the population parameter is 0.132, 13.2%. Remember, we use P in this case to determine the population proportion because we have the proportion of pennies. 13.2% of pennies were made before 1982 that are still in circulation, and the remainder, the other 96.8% of pennies would be post-1982. What is the statistic here? 11 over 50. And we're going to call this P hat. P hat. That means it's my statistic. I didn't calculate this from the whole population of all the pennies. This was calculated from that sample of 50 pennies. 11 out of those 50 pennies were pre-1982. That comes out to be 0.22. So that is the P hat. Does Jenna have at least some evidence that more than 13.2% of her pennies are pre-1982 copper pennies? Does she have some evidence that her pennies have a greater proportion than 13.2? Why or why not? She can generalize to her pennies, right? Because she took a sample from her pennies. Yes? We don't know. She just has a container of pennies. It's a big container. It's like a change jar at home. Everybody just throws it in. It's about this big. I don't know how many pennies are in there, but there's a lot, right? She just took a sample of 50 out of there, took her little cup, scooped it in, got a random sample of 50 pennies. Would we say that she has some evidence that more of her pennies are pre-1982? Why or why not? Yeah, her mean was 22%, right? The population mean is 13.2. If her sample matches the population, she should only have 13.2% of her pennies being pre-1982, but she came up with 22%. So I do think she has some evidence. 22 is bigger than 13.2. So what could be a reason that her proportion is bigger than the population proportion? I want two different possible explanations for why her percentage is higher than the population average. Yeah, maybe she got lucky. She got lucky in her sample. Maybe the average in her jar really is 13.2%, and she just got lucky. Some old pennies got thrown in on top, and that was included in her sample. What's the other possible explanation here? So this is kind of the same as saying this just happened by chance. This is a fluke. Not necessarily. Like what reason would you use then? Sorry, I like what you're saying. Just give me a little bit more. Yeah, maybe the percentage in her container really is bigger than 13.2. So either what she observed happened by chance, or it could be that there really are more older pennies in this container. So then we have a sampling distribution. Technology was used to simulate selecting 100 simple random samples of size 50 from a population of pennies in which 13.2% are pre-1982 copper pennies. So the dot plot shows our simulated sampling distribution. There is one dot on the graph right here at 22%. What does that dot represent? There's Jenna's result right there. We're going to finish this up tomorrow and then roll into our next lesson. What's due tomorrow? Homework. Homework is due tomorrow. If you need another copy of it, please come and see me.